In this video, we are going to explain our work, Coherence as Texture. Stereo imaging is the most classical algorithm for passive 3D reconstruction. Given the scene captured from two angles, it matches feature points into images and calculates the depth from disparity between points. However, what if the scene is textureless? You won't notice any camera view changes until you see the boundaries. Till now, there are no passive 3D reconstruction methods that can deal with the texture's target. In this work, we propose an optical way to match points in stereo images without the need of textures. To explain it, we start by explaining some wave properties. When an object is illuminated by an area light source, each point will reflect a unique wavefront. For waves from the same point, their wavefronts are the same and thus have a fixed phase difference, or say they are coherent. On the other hand, if two waves are from different sources, their wavefront will be incoherent. We can observe coherence by interference. To be precise, when we force different delays between two coherent wavefronts, they can constructively or destructively interfere and thus have different total intensities. However, when waves are incoherent, since their relative phase changes over time, their total intensity remains the same regardless of the delay. In short, we can recognize coherent waves by observing total intensity changes with different phase delay. We can use coherence to find point correspondence between two views. Note that under natural illumination, each scene point is only coherent with itself. Thus, if we can optically overlay two views, the points overlaid with itself should interfere. However, in this way, interference terms from nearby points can cancel each other as they have different relative phase. Thus, we need to make sure only a few points can be interfered with at one time. One way to do it is to optically flip the view 2 and interfere with view 1. So only the points overlaid with itself as on the white line can be interfered. It means we find correspondence in two views and thus can solve depth from disparity. If the overlay is shifted by a different amount, we can isolate different scans of points and find their correspondence. Overall, we need 4 optical operations: flip, interfere, tilt, and shift to fully reconstruct the 3D target. In the later slides, I will go over how to implement these 4 steps optically. First, we use a retroreflector to flip the scene. Compared to the 4F systems with a mirror in the center, the one with the hollow roof retroreflector flips the scene in one dimension. To overlay two scenes, we first rearrange the left setup to bring the mirror to the bottom, and now these two systems can be implemented in one setup. By adding a translation stage, two passes can now be interfered with different path delays. Put it between target and sensor. This setup can isolate points by flipping and interfering. But note that our goal is to measure depths from disparity. So, for target at different depths, we want to observe light only from tilt angle, so the pattern shifted depends on the depth. To limit the light ray angle, we can put a shifted aperture in our 4F system, which is also known as a tilted orthographic camera. Combined all together, our system can now interfere view 1 with flip view 2. Finally, to shift the scene to scan different parts, we add a relay lens in between so the scene shifted when the lens translated. We built a hardware prototype in our lab to implement the above design. That summarizes the full pipeline of 3D reconstruction. Suppose the camera only sees the clear region of the target, then the captured images are almost uniform. However, we can calculate the interference signal out of the images, extract the line position, and calculate the depth of one scan from disparity. By combining multiple scans, we can get the depth map and reconstruct the 3D target. Under an ideal light condition, we can reconstruct shapes such as a cylinder with a sub-millimeter resolution. While our setup can image a tilted plane under indoor white light, in the target region the camera sees, the plane is totally textureless, but we can still reconstruct its depth map. We also move our setup under sunlight and reconstruct targets including the head of screwdriver or multiple planes. For more details, please refer to our project website or come to our poster session. Thanks for your attention.